Hello, fellow Idaho students. My name is Robert Bolaños, and this is my presentation for project presentation number 1 for Antenna Principles and Design. Right now, this thing does not have a title at this point, though. This is just a stationary title at this point. Until the final product is done at the end of the semester, this will have a title of its own. So as of right now, for just this project presentation, it's going to be titled as Project Presentation Number 1. So to kind of get in a better understanding of how my PowerPoint slides are, and as far as like what my topic is right here, I've also presented my table of contents, and these are pretty much the topics that I wanted to go over with you guys as far as what am I looking at and as far as addressing with you guys regarding on my topic. So, we start off with wireless communications because this is actually the main topic though here as for our project is concerned and what it's pretty much addressing in this case. So wireless communications was actually introduced at around the 19th century, and throughout those years, wireless communication technology has developed over the years. For example, throughout those years, phones were always hung on the walls and they weren't portable during that time. Now in today's society, you can actually bring your iPhones or any kind of phones or cellular phones anywhere you want to go in this case. So that just shows how well wireless communication technology has advanced throughout the years. And this type of technology incorporates the communication between two or more devices using a wireless signal through wireless communication technologies and devices. Wireless communication generally works through electromagnetic signals that are transmitted by a device within the air, any kind of environment, or even an atmosphere. The communication between the two devices occurs when the destination or receiving device, that's the word choice that I'm using, captures these signals, which creating a wireless communication bridge between the sender and the receiver device. In today's society, the wireless communication technology has been evolved with a variety of wireless communication devices and technology ranging from smartphones to computers. You also have like tablets, you have laptops, you also have Bluetooth technology, and even printers. But also, wireless communications has various forms of technologies and methods besides just all these other devices that we use for today's society. Certain types of methods and technologies that wireless communication is involved with is satellite communication, microwave communication, and infrared communication. So pretty much these are the types of wireless communications that I just mentioned, and pretty much satellite communication is one of the wireless technologies that is widely spread all over the world, allowing users to stay connected virtually anywhere. So this type of technology works when a signal is transmitted near the satellite. And when this happens, the satellite then amplifies the signal and returns that transmitted signal back to the antenna receiver, which is located on the surface of the Earth. This type of signal can contain information such as scientific data. It can require the help of the satellite and also where the satellite is currently located in space. But a really good perfect example as to how this technology works, and this is a really if you're a visual person like myself here, this is a very perfect visual example to see how this technology works if it's hard to understand it, is how you can think of it of how bats communicate in the dark and the way how they're able to use what's called echolocation. And this is a perfect example of a transmitted signal, because what happens in this visual example is that when the bats travels at night, it's going to pretty much let out a screech or like a scream, which will generate vibrations or waveform vibrations. When those waveform vibrations hit an object like a tree, for example, those waveform vibrations will transmit back to the bat with the use of its ears. And this type of technique is how bats can see in the dark. So this would be a really good example of how, like I said, as far as how satellite communications work, basing on if you can visualize how bats use echolocation. Infrared wireless communications communicates information in a device or system through infrared radiation. And if you was to ask me what is infrared radiation, The answer is that this radiation is made up of electromagnetic waves at a certain wavelength just beyond what we could see on the red side of the spectrum, or should I say the electromagnetic spectrum. Infrared radiation lies between microwaves and visible light and can be used as a source of communication, such as with mobile phones. You can have it for TVs, security systems, and laptops. Then you have microwave wireless communications, and this one uses radio waves to transmit information, and the wavelengths of radio waves are basically measured in centimeters. In this communication, the data or information can be transmitted using two methods. One is the satellite method, and the other is called the terrestrial method. The difference between these two methods is that the satellite method is when data can be transmitted through a satellite with a typical frequency ranging from about, I want to say, between 11 gigahertz to 14 gigahertz. And the terrestrial method, on the other hand, is when two microwave towers with a clear line of sight between them are pretty much used, and they basically have a typical frequency range of about 4 to 6 gigahertz. However, the main disadvantage of microwave signals is that they can be affected by bad weather, especially the rain. And if you was to ask me, so how is it that rain could affect microwave signals, which is pretty much a really good question. The answer to that, what I found out, is that the larger the drops and the amount of rain that is being produced, the more that the cell signal is going to be scattered, meaning here that the rain could actually weaken your cell signal more than any other weather in this case. And the theory behind this one is because the high frequency wavelengths used by cell phones, they don't travel well through water, because water, as we all know it conducts electricity, and it could reflect radio waves. Also, water vapor absorbs the energy of radio signals and turns them into heat. So basically, water blocks the radio signals between the tower and your cell phone. And another thing, and I know that a lot of you guys in Idaho have experienced this type of weather, which is snow. I don't get that here in San Antonio, here, that's a matter of fact. But snow is also another thing that can also affect microwave signals, because ice crystals are far less dense than water, especially when they're in a form of a snowflake. So they don't have nearly the same effect on signal propagation. However, if you have heavy amounts of snow, that may still refract radio waves, and that can even reduce signal strength as to how that would be used, as to how it would affect radio waves. So, antennas are pretty much devices that converts radio frequencies, or RF fields, into alternating currents, or should I say AC current, or vice versa. Antennas are constructed with the use of metallic conductors with an electrical connection to receivers or transmitters. And the current the current within antennas is pretty much forced through these conductors by radio transmitters to create alternating magnetic fields. And these fields causes induced voltage at the antenna terminal, which are connected to the receiver input. In the far field, the oscillating magnetic field is coupled with an oscillating electric field, which defines the electromagnetic waves capable of transmitting signals for long distances. Antennas, they're pretty much used in wireless local area networks. They're used for mobile telephones and satellite communication, as I just mentioned. However, for this project, since the focus is primarily on wireless communications, there are various types of wireless antennas that are available in today's market. There's like a variety of them. But some of the most important types of information that I thought that maybe was more significant, that could be significant within this area, which is mobile wireless communications, are the omnidirectional antenna, you have the directional antenna, and then you have the highly directional antenna. And the difference between these three is that the omnidirectional antenna is pretty much used to send and receive transmission signals from all directions. And this antenna does not require any specific direction, since its radiation is about 360 degrees. So typically these antennas if you was to ask how do these antennas look, like what would they look like? The answer to that is that these antennas, they kind of look like long flat sticks that act as a main antenna, which is actually used to distribute signals to other computers and devices. That includes wireless printers, you have PDAs, and etc. Directional antennas, are used to cover the signal in a particular direction, meaning that now that there's a certain direction here that it would have to go, as opposed to the omni, which is pretty much where now all the signals are coming from all directions. And this antenna has various structures, and one of the most popular ones that I've seen a lot, not just in my work but also in today's society, is the Yagi antenna. And then you also have the helical antenna. So those are various structures though that directional couplers can be composed of or be packaged though here. And these antennas can be used in a variety of applications. And then finally you have the highly directional antenna. And this offers numerous benefits. There's like a whole bunch of benefits you can use with this one. I won't get too much into detail on this presentation though here, but trust me, there is a lot if you look it up. And it's pretty most effective at transmitting signals in one direction effectively, which is one of the benefits that it makes it. And it contains two different types of antennas, and one is the grid antenna that can be seen on the top of a television set, and the other is a dish-shaped antenna, which is mainly used to receive satellite TV stations. So this was our project that we were assigned, or one of the topics that we were assigned to. And it's pretty much stating though here that with the widespread of wireless communications devices, there's an ever-growing demand for portable, low-cost, and easy-to-use devices that are capable of evaluating the electromagnetics performance of antennas or wireless devices and systems. Conventional measurement systems are very accurate, but in the meantime, they're also bulky and expensive. This limits their use in field measurements in classrooms as well as in everyday life. Our goal is to design and build a simple portable system to visualize in easy way the properties of an antenna system and provide educational material to explain these properties to non-specialists. And certain specifications are you can actually make a proposed setup to demonstrate one or more of the following properties of the antenna systems. Here we are, that we have. And the results should be displayed in real time. The setup must be designed using non-dedicated and non-specialized equipment, and I am encouraged to use either mobile phones, small drones, or any commercially available devices that is not specifically intended for antenna and RF testing. The setup and procedure should be easy to understand for non-specialists, and the setup has to be easy to reproduce in a classroom or at a home. I should also develop a step-by-step instructions to allow anyone to reproduce the system, and you should be able to explain the theory behind the demonstration setup in a simple way so that other non-engineers are able to understand it as well. And so that's pretty much the assignment or the topic here that I had chosen, to be honest. Now, for my presentation and for my project, I've decided to do two topics, two of the following properties. Mine is going to be, I like to focus more on the antenna gain and also the beam width. And those are my topics that I'm pretty much wanting to use or demonstrate here in this case for my project going along. There might be others that could change in a bit here, or I could add, but it really depends on pretty much the research that I'm really able to find. So, antenna gain. The antenna gain is defined as the ratio of the power gain in a given direction to the power gain of the antenna. The antenna is expressed as the following equation, which is this one right here. And pretty much based on this formula, if you just use observations, you can tell that the isotropic gain right here that you see has an inverse relationship within the formula of the gain in dBi, because if we increase the isotropic gain of an antenna, this would decrease the gain. However, this ratio this is the ratio, and if we learn this right here going into our first midterm exam, this ratio, I'm pretty sure you guys are familiar with this, is actually the numeric this ratio of the numeric gain and isotropic gain would become pretty much dimensionless, which is basically the conversion which is basically the converting the dimensionless antenna gain into dB is what it is. So one of the gains that was being talked about in our lectures and what we have been taught very specifically is the realized gain, which is calculated by considering the total efficiency of the antenna along with its directivity. The total efficiency of the antenna is considered as the losses due to reflections at the input terminals, as well as losses within the structure of the antenna. The total efficiency formula is written as this formula right here, where this ER term right here is the reflection mismatch efficiency. The ED is pretty much the dielectric efficiency, and this EC terminal right here is pretty much the conduction efficiency. However, if you factor in the dielectric and conduction efficiencies, they're usually grouped together. So they're measured and known as ECD, which is this term right here, which is ECD. And so therefore, when you're grouping those together, that's where your total efficiency may be written in this format or in this equation right here. And therefore, the realized gain is therefore calculated by using the total efficiency and the directivity, which is why you're able to get this formula. And pretty much the realized gain and the directivity, they're both specified in dBi. The voltage reflection coefficient is in dBi, and the efficiency as a value, and the efficiency would be a value anywhere between 0 and 1, I would want to say. So beam widths is defined as the angle between the points in the main lobe that are located down from the maximum gain by 3 dB. The beam width can affect the antenna, and if you was to ask me how would the beam width affect your antenna, like what can it do? The answer to that is because if the antenna has wide beam widths, then what would happen is that now you're going to result in a low antenna gain value. And antennas with narrower beam widths tend to have higher antenna gain. So you have to remember that with wider beams, the lower the antenna. If you have narrower beams, that's going to really increase your antenna gain. But it really depends on how narrow and how wide you're going to be doing that in order to affect your beam widths. But you also have to keep in mind that antenna gain measures how much power is radiated in a given direction. So an antenna that directs most of its energy into a narrower beam, that will have a higher antenna gain though here. So my homework that I have to do with this project, though, like I said, when I say by homework, meaning that this is more of the research that I'm still continuing to do. This is more of the stuff that I still need to figure out and kind of research and kind of answer these questions, though, here further on. So for homework, my homework for this project is to figure out what kind of antenna I really like to design in the wireless communication department, because I know that there's a variety of antennas that I could model. But for this assignment, I would need to design one specifically within the wireless communication department. So therefore, I would need to do a bit of research as to how each antenna can be fitted into wireless communication applications, how is it used for, and how is it right here that it could be used in today's society, and also if it could be possible though here, could it be up for any design or future considerations further down the line. And then my next thing I got to figure out is pretty much designing the system, because for the final project, as I've already mentioned, I would have to for the final project for me personally, I will be able to show the schematic, my schematics, and also show the results such as the voltage, the current, and etc. to show how the system will operate under certain variables such as like time and frequency. And I'm willing to use, I believe it's the network, that network or our simulation software that we're using, or another thing that me and my father have been using for quite a while is called TopSpice. And I'm willing to show a demonstration once I get this done. I'm willing to show a demonstration of how of all the stuff here about voltages and currents and maybe even impedance though here once I get to that stage though here. So. Yes, this actually concludes my presentation though here. If you guys have any questions, please email me back. Other than that, this concludes my presentation though here.